Here we introduce a new quantity, which we call the momentum of a particle. The momentum of a particle is defined as the mass of the particle multiplied by the velocity of that particle. Momentum is denoted with a lowercase p. There's no special meaning to that p other than it's not used in many other places, and frankly we're running out of letters at this point. Momentum is made up of mass times velocity. Mass is a scalar and velocity is a vector. When you multiply the two, you end up with a vector, and so momentum is a vector with units kilogram meters per second. There's no special name for the units of momentum other than the fact that it's made up of mass and velocity. Momentum is a vector that points in the same direction as the velocity vector. We'll see that typically we'll take the momentum vector and decompose it into x and y components. Momentum is a reformulation of Newton's second law. Newton's second law tells us that force equals mass times acceleration. However, that acceleration is the derivative of velocity. Assuming that the mass of an object is constant, it doesn't matter whether that mass is on the outside of the derivative or the inside. And thus we see that the force is the time derivative of this quantity, which we call momentum. On the other hand, we can look the other way. We can integrate both sides with respect to time. If we integrate the derivative of momentum, we'll just get the change in momentum back, presuming that we integrate from an initial to a final time, an initial and a final momentum. If we integrate force with respect to time, we get this quantity, which looks at the amount of force that's applied over a set amount of time. This quantity, the force times the time over which that force is applied, is the impulse. The impulse is the area under the force as a function of time curve. The impulse is the force times the time, or if the force is changing, the integral of force with respect to time, and the impulse is the change in momentum. Impulse has units of Newton seconds, which if you decompose newtons, you'll see have the same units as momentum. This brings us to the other origin of this idea of momentum. If we think about our kinematic equations, one of them told us that the final velocity was the initial velocity plus acceleration times time. Or if we bring the initial velocity over, we can rewrite that as the change in velocity is the acceleration times time. If we multiply through by a factor of mass, this mass times velocity, again, if the mass isn't changing, this is our change in momentum on the left. On the right, if we combine mass and acceleration, that is giving us our force times time. And so our momentum is defined as it is, as the mass times velocity, so that the change in momentum is what happens when you apply a force over an amount of time. We can sum up what we just mentioned using the momentum principle, which says that if a particle experiences an impulsive force, that is a force that's applied over an amount of time, that impulse will be equal to the change in the particle's momentum, or the change in momentum is equal to the impulse felt by that object. Here we're writing it as in the x direction, but in fact momentum is a vector quantity, impulse is based on force, which is a vector quantity, and in fact this vector in 3 dimensions must equal the impulse vector in 3 dimensions as well. We compare here the parallels between the momentum principle and the energy principle. When we looked at energy, we looked at a force that was being applied over a distance. This was the work done, and the work was a change in the energy of the system. Now we're considering a force that is applied over an amount of time. That is the momentum principle, and that's because the force being applied over a time is the impulse. And so we see the parallel between the two. You have a change in kinetic energy is work done, which is a force being applied over a distance. A change in momentum is an impulse, which is a force applied over time. In reality, when you have an object that's acted on by a force, this force is doing work, and it's creating an impulse at the same time. If you're applying a force to the object, you're applying that force over an amount of time, and the object is going to accelerate, and so the object will be feeling that force over a distance. And so these two, not only do they look parallel, but in fact both of them are occurring at the same time. They're two separate and parallel ways of representing the motion of an object. They're a little bit different. For example, energy is a little bit easier to deal with because force is a vector, displacement is a vector. When those are dotted, you get work and energy, which is a scalar. Those are numbers, and so those are a little bit easier to deal with, but we've lost a lot of the information about the time. When we look at momentum, we have force, which is a vector, times a scalar, and so impulse is a vector, and momentum is a vector. So that holds on to the time and the directional information, but it makes the math a little bit more difficult. When we want to study the motion of an object, you can use either the energy principle or the momentum principle. Really, which one you want to use or which combination depends on the question you're trying to answer. We've seen how to use the energy principle before. We'll see here what we can do with the momentum principle, and we'll see how to use these two terms either separately or in concert with each other.